So now we're into the what I call the lightning round of quick talks on really important topics. We're going to do a deep dive with each of these speakers individually. I called the panel Reimagining because each one of these people, I think, are reimagining a future, whether it's materials or water or the entire built environment or pollution. So we're going to have some fun listening to them. First up is Garrett Benisch. Garrett is a designer working to bring new impactful materials to scale. He graduated with a master's in industrial design from Pratt, where his thesis project, Some Waste, that's S-U-M, imagined new products made from wastewater solids. This project led him to develop a role at Bioforcetech in 2020, where Garrett has been developing the brand direction, applications, and partnerships for OurCarbon, a fixed carbon made from sewage sludge. Garrett is propelled by the notion that waste is simply a category and believes that we are capable of a waste-free future. And I'm going to let him tell you about OurCarbon. So Garrett, why don't you come on up?
Thank you. I brought goodies, so I need to be able to walk. Let me just grab the first one. So now that I kind of already let the cat out of the bag, but yeah, I think we started in the middle. So that's okay. Let me pass this around. You already know what it is now, so the secret's out, but still worth a smell. So I want to start by just giving a sense of the sort of ecosystem. So I've been working on this since 2020. I did not develop the technology. That's really hard to do. I'm just doing the material side. Kind of hard, not that hard compared to this. Bioforcetech Corporation, since 2012, has made this amazing technology that can process any organic at net zero energy and end up cleaning and fixing the carbon in it. I'll explain it a little bit on the way, but that's the sort of parent company. OurCarbon is the brand for the material that we're producing. And so we've been developing this material for about 4 years. I always like to start with this graph because it really is what we should all be sort of waking up and looking at for breakfast every day. And this is our path to net zero according to the IPCC that we may or may not be on. And you can see here, we have our business as usual emissions, right? So we all know that we need to be cutting these emissions. As we cut those emissions, we will be lowering our overall net emissions, hopefully to zero. But as you know, many of you working in architecture, we have this chunk here of hard to abate sectors. Energy, steel, cement, things like this that take a lot of heat and have even minerals that break off and form CO2. So these negative technologies, right, afforestation, restoring wetlands, the natural carbon sinks are the strongest, but there's technological carbon sinks that need to be formed to compensate for the emissions that will be remaining. Most important thing to remember is how small this is, right? I love what I'm doing, but it's really the last bit. What we need to do every day is cut into this green section. And so what I love about not the material, but the whole process and where it's located in its ecosystem is that we are really contributing to that green section making its way down. So OurCarbon is pioneering the production and application of carbon-negative materials made from organics. And we have this sort of impact in 3 stages. We divert organics from harmful and emissive practices going on today to help cut into that green area. We transform them into this fixed carbon using our technology to help with that negative area. And then we apply it in ways, this chair might look familiar from earlier talks, we apply it in ways that replace fossil fuel equivalent or chemical intensive or toxic materials to, again, avoid more emissions and move that green section down. The way that we can make the biggest impact is by prioritizing what you process. What you choose really matters. If I take a virgin wood waste wood chip, right, and bring it all the way down to this carbon, I'm skipping lyocell, tencel, bio-based plastic inputs, compost, mulch, animal bedding, all of these things that is not in my list that we can add, and you're really downcycling it into this carbon. If I take sewage sludge, biosolids that's currently contaminated, that currently goes to landfill, contributes to methane or adds toxicity to our ecosystem and bring it up to this carbon, we're adding value and not taking away from another place. So we really prioritize what we call impact feedstocks. So biosolids is the residual material that's made at the end of any wastewater treatment process. It's made around the world, obviously. It's actually remarkably consistent, and it's made year-round. In the US, almost a third of all biosolids go to landfill. And when you put anything organic in landfill, especially something as bioavailable as this, it emits as methane. So methane is obviously 84 times the global warming potential of CO2 on a 20-year period, and all the value in the material is lost. You do control contaminants. Biosolids has PFAS in it, it has heavy metals in it, it has microplastics, pharmaceuticals. Any pill you take, you pee out about 80% of. So you do control those contaminants, but you emit a ton of methane. About 14% of all US methane is from landfill. If you do a study like we did, looking at where this methane can form in its highest quantities, you can split the country up into 4 regions. So the most humid and the most hot, and then the least digested biosolids will have the most carbon in it. Is sort of the way you can turn that dial the most to see how much methane you can avoid by taking that material as an impact feedstock. Our first system is right here in Redwood City from Silicon Valley Clean Water. That's what you're smelling right now in that jar. We have a system in Redding, California, right on the border of the cool, wet climate, and in Ephrata, Pennsylvania, that are starting up right now. Over there, when we make a ton of our carbon, we avoid 10 tons of CO2 just from avoiding biosolids going to landfill. If we go to this most emissive area, if we were to target the panhandle of Florida and New Orleans, where you have some pretty unregulated landfills and unregulated biosolids and hot and humid areas, every ton of our carbon that we make would avoid 24 tons of CO2. If you drive a car, you emit about 4 tons a year. So, and our system's around 300 tons a year base level. So it's about a ton a day that we make, taking 5 or 6 cars off the road for a year, just by choosing this material instead of another one. Land application is what happens to most biosolids. I think you can imagine the downfalls of that. There's a little bit of phosphorus, nitrogen, carbon available in the material. There's also all the things that I just said. Luckily, regulation around PFAS, they just got a Superfund designation as of July 8th. PFAS in biosolids is starting to cut the tap on this. It's great that these things are stopping, but the wastewater world is freaking out. Since the Clean Water Act, this has been the only way that they could survive or put the material somewhere. So we're really excited to be able to offer a solution. So we have a 2-step technology. I'm sure there'll be questions after, but I'll describe it just really briefly. The first step is drying the material biologically. So if you have a material that's so wet, we take dewatered material. It's known as cake, biosolids cake. The material is 20% solids. That's the best they can sort of do with centrifuges. So it's 80% water. If you want to get the water out of that material, it takes a lot of energy. Natural gas or electricity and a belt dryer or a drum dryer is the way of doing it. It's continuous. It takes a lot of natural gas. If one little rotor breaks, the whole thing shuts down, et cetera, et cetera. So the first machine that Bioforcetech developed is the biodryer. So instead of doing that, we fill these sort of containers with 8 tons of cake, and then we pass air just from outside through the bottom of it to basically create a speed composting environment. So the bacteria, I think of it as a nightclub. You get the music going, you serve the right drinks, the lights are just right, the bacteria start partying, and the sweat starts coming out, right? So they basically create enough heat to evaporate the water. You guys are a good audience. So they make enough heat to evaporate the water out of the material. It is time competitive. Exactly. It's time competitive, so it's about 50 to 72 hours for those 8 tons. It's the same if you were doing a continuous line, but it's really resilient. They're modular. We put them down in line. You can use each one and taper them and store solids. At the end, the lights come on. It's kind of last call, but people still want to party a little bit, but there's a little bit of water left. If you just have a dryer, we need to use natural gas to finish it off. If you have it in that scenario, it's still 30% of the normal energy load. But our second step is what takes care of that. I don't have a photo because it was a proprietary machine until about a month ago, so I don't have a photo up here. But the second process that we undergo is called pyrolysis. I can actually show you the system up here. So when you heat a material, it's down here kind of hiding. When you heat a material out in the world, light it on fire, the carbon burns off and forms CO2. If you deprive that material of oxygen, some of the carbon will form a gas that can be burned for heat, and most of the carbon will be so excited to try and latch onto something, but there's nothing available, causing it to bond to itself in really tight chains. It's called pyrolysis. There's a myriad way of doing it, from dumpster fire to controlled way right now, if you Google it. We're at the very far end of that spectrum. So we feed biosolids in dry, bring it up to 450 to 650 Celsius. It lets off that gas. We recirculate the heat from burning that gas to keep it at temperature, give the rest to drying to finish off that bit after last call at the party. And you end up with a really clean, consistent, contaminant-destroyed material. We've been published by the EPA to even destroy PFAS in the biosolids. So you have this material that's rife and hard to collect and percolating into all of our environment, that actually this is a really rare catch point that we can now say, give us your biosolids, we want to take the PFAS out. We're certified bio-based. We're Bay Area Air Quality Management District permitted, which was really hard, took about 4 years. But we have really great emissions controls. And our products that we use out in the market can be used on baby clothing, European food containers. It's a really clean material. So the part that I deal with. The first way that we use our carbon is as a pigment. So this stage, that camera, the car tires you drove in on, this remote, it's all colored black with carbon black. And this is now that apply stage, right? So carbon black is basically made by burning bunker oil in a kiln that makes as much soot as possible. And that's what's used in all of these products. So this might look familiar from Kelly earlier. This is model numbers, Esker chair. They do make them bigger. We're model numbers exclusive black, so we are able to keep their product line bio-based with our black pigment. These are from Covestro for car interiors, huge company out of Europe. This is Wearlight in Spain. They make bio-based polyurethane foam that we're coloring black as well. And I'm wearing Virus Inks Rethink Black, which is a water-based and bio-based screen printing ink that we exclusively tint black. We're an ingredient brand, right? So I can't make something out of our carbon, so what I'm inside of is really important. So people like Model Number, Virus Inks is a really, really awesome group to collaborate with so that we can keep our values retained. Carbon black emits about 3 to 5 tons per ton of production. So if you're doing the math now, we're up to like 30 tons per ton of our carbon that goes into that use. I had slides. I should have been clicking. We work in denim, in fabric dyes, polymers, model number. So the last part, and the reason that I was late today, was because we poured our very first Bay Area concrete pour using our carbon. So if you notice that our carbon kind of looks like a black sand, exactly. It's about 65% silica, 30% carbon, which means that uniquely to this material, we can use it as an aggregate replacement in structural grade concrete, where it will retain the structural performance, but pound for pound pump carbon negativity into the built environment. This is a 3,000 PSI type 1L and SEM cement. It's got about 150 pounds per cubic yard global warming potential. We have over 100 pounds of our carbon per cubic yard in here, bringing it down to under 50 pounds per cubic yard. Cities like New York have some of the strictest carbon thresholds for concrete that are asking for a reduction of 10%. So that's, after the already reduced amount, over 2/3 reduced. And this, for proof, because I was late for class, is from today's pour with Central Concrete and SOM, actually, for the Head Royce School in Oakland that we'll be pouring in a couple of weeks. That was our first project in Oregon at a winery. And yeah, that's what we're working on. Much more to come. We're also looking at other feedstocks. What else can you, if you process something else at different parameters, how can you make designer carbons? So we're partnered with the USDA, processing agricultural residues, paper mill sludge, things like that, to actually fine-tune carbons for different uses in batteries, photovoltaics, pigments, things like that. So this is sort of the start for what we hope to be a designer carbon production. Thank you.